Hi everyone, welcome back. So in this video, I thought we will discuss how to simulate ISF and PPV using PXF and PSS. So if you've been watching this series, I guess, we discussed in the last few videos what is ISF function, how to simulate it using transient response. And we also discussed the theory behind PPV function, but we haven't really talked about how to simulate it. So in this video, let's do that. And since we discussed how to simulate ISF using transient, the problem with that was that it's too slow, right? It takes forever to run that transient simulation. So I thought, okay, in this video, I'll show you how to simulate it much faster using periodic steady state and periodic transfer function. So in this, now it becomes sort of instantaneous. You can pretty much in 1 or 2 seconds, you can simulate the ISF, right? That's very useful since we'll use these concepts in the future. So let's do it. So we'll call this ISF and PPV simulation using periodic steady state and periodic transfer function. Okay. So before we actually go into Cadence and do the simulation, I think it's better to kind of briefly talk about what is PXF, why it's able to simulate ISF very well, right? So that's a useful thing. And PXF is usually implemented in many simulation softwares. Cadence definitely has it. So let's go ahead and see what it is. So if you don't know what ISF and PPV are, I'm not going to review them in a lot of detail. So I highly recommend you go watch the previous videos and come back here. But if you don't care about the theory and you just want to know how to simulate this one thing, that's still fine. You can just watch. Okay, so periodic transfer function. So here I'm going to focus on maybe the cadence implementation. And this is generally used to simulate linear periodic time varying systems. At least in this case, that's what it's doing, right? So an oscillator we discussed is a linear periodic time varying system, right? Okay, so PXF is a transfer function. So if I had a linear system, then the linear system can be characterized, if it was LTI, linear time invariant, not just linear, then we know that whatever input you put, let's say you have some input current and you're looking at the output voltage. If this input current, say this is the input and this is the output, if this input current was at some F in, then we know that its influence will only be at F in at the output, right? So there's no translation of frequency when you have an LTI system. Whatever input frequency you have, that can only influence the output frequency. Whereas in an oscillator, it's not an LTI system, it's actually a nonlinear system, but ISF kind of assumes that the transfer function from the input current to the output phase is linear, but not time invariant. It's a linear periodically time varying kind of function, LPTV. So for LPTV, what you get is something like this, right? So let's say if I have an LPTV and this LPTV has some internal periodicity at omega naught, let's say, some kind of switching from F to omega. Omega is 2 pi F. And I have some input frequency at F in, then the output would actually be at all the harmonics, right? So all kind of combinations of these two. So M times F in plus N times F naught, right? Yeah. But typically, if your Fn signal is weak, right? So if your Fn is, the amplitude of this Fn signal is small, which we will actually assume in our case, then the outputs would be only at Fin plus N times F naught, right? So it's kind of how mixers work. And we'll discuss mixers later, but that's kind of what happens in an LPTV system. The way this is kind of characterized using periodic transfer function is that it's sort of flipped. So you have an LPTV system at some omega naught, and the input now has harmonics. So the input is at, maybe let me actually make this a little bit more clear. So I'll call this F naught, so that we're not going back and forth between F and omega. This also be F naught. Okay. So if the input is at some K times F naught plus delta F, right? So then this mixes with F naught, and we're looking at the output at F naught plus delta F. Okay. So we just want to characterize what is the transfer function from all of these harmonics that are offset by delta F down to one of the outputs, which is at F naught plus delta F, right? So that's the transfer function that PXF simulation kind of computes for you. So it's probably good to kind of look at this pictorially a little bit. So let's do that. So let's say this is my frequency axis, and that's zero frequency. And let's say, okay, my omega naught or F naught is here. I'll call this F naught. And then I have obviously the harmonics of F naught. So there's one there, one there. And we'll also consider the negative frequency. We'll see what that is. Okay, and that's my input. And then I have output, which again has F naught, right? And then I say, okay, now I have a delta F offset. This is delta F. And I'm injecting a sinusoidal signal at here, at this frequency. And I want to see what happens at this output. Right? This is also a delta F. But I also want a transfer function from this sinusoid, from this sinusoid, this one, this one, this one, and this one, and so on, right? So that's what K determines. So here K is equal to 1. Right here, K equal to 2, K equal to 3, and this is 0, -1, -2, -3, and so on, right? Okay, so your periodic transfer function tells you what is the transfer function from all of these inputs to this single output. Okay, so you have many transfer functions essentially. So this will be h of -3. This would be h of -2, right? H is the transfer function. H of -1, and h has an amplitude and a phase, right? So what is the transfer function from this input down to here? So that will be one amplitude and phase. How does that sinusoid change? We'll look at some equations, but essentially that's what PXF is doing. Okay, and mathematically you can actually show that there is a relationship between this negative frequency and this positive frequency. Okay, well, the negative and positive side. So if you have a real signal, then this whole negative frequency, the negative frequency components can be folded onto the positive side. So these are the positive ones that we had. This is 0, and the negative ones show up somewhere here. Right? So it's like folding this with respect to the origin, and then folding this, and so on. Hermitian symmetry is what they satisfy, and you can kind of show that. So essentially, now we're looking at the transfer function from these guys. Right? And when we simulate it in Cadence, we'll actually see the spectrum only on the positive side. And that's why I'm kind of writing it out like this. Okay. Again, remember this is 3, this is -3, this is 2, -2, 1, -1, and 0. Okay. All right. I want to make one further comment. So we said that, this indexing is based on K, right? So here K is 3, 2, 1, and so on. It's 3, 2, 1. But the way Cadence indexes it is a little bit different. So I just want to point that out. Okay, so the input we said was K. I'll actually switch to omega at this point. That'll be more useful to us. It's K omega naught plus delta omega, right? But in Cadence's case, it actually uses P omega naught plus delta omega. So it says, okay, I have a fixed output. This is omega out. And my omega in is shifted from the output by P times omega naught. So this is omega in, okay? Which just means that P, as we've written it above, is K minus 1, right? So P is actually the index that you get in Cadence. And we'll see that when we run the simulation. Whereas you have to keep in mind that this K is your typical index. This will actually be the index in the ISF. Okay, so with that in mind, let's quickly move on. I want to move to the simulation part. But it's important to see how PXF is actually producing the ISF, right? So we'll do a quick review of ISF. So we said that, okay, ISF is what? You have an input signal, which is like a pulse, let's say, current, charge. And then you have a linear periodically time varying. This is actually the ISF model, right? Transfer function from the input current to the output phase, which is phi of t. And then phi of t. And then this is put into a nonlinear transfer function, right, which is the phase modulation part. And then that gives us the output voltage. Okay. And this whole thing is what we will simulate using PXF. So we need to kind of establish the relationship between the two, right? And we'll actually assume that this, as long as this modulation index or the signal strength is weak, this phase modulation is not exactly, I mean, it's still nonlinear, but we will kind of make an approximation and make it a little bit simpler. We'll see. Okay, so let's move ahead. Okay, so if I have I of t, it of t, which is the input, is a sinusoid, it, let's say cosine of omega naught plus delta omega times t plus gamma k, which is some arbitrary phase, plus k minus 1, which is actually the p, right, coefficient, times omega naught t. I mean, this is essentially just cosine omega naught, cosine p, k omega naught t plus delta omega t plus gamma k, right? So that's the injected impulse, injected sinusoid at the input. And we can write our ISF as a Fourier series, right? We did this already in the ISF video, so I'm not going to describe where that came from. But this is sort of a generalized Fourier series in terms of cosines. Cn cosine m omega naught t plus theta m. Okay. So if you have these two, then we can get this phi function, this one, by convolution, right? It's not exactly a convolution, I guess, but it's a convolution integral of some kind. It's an integral. You can think of it as a time varying convolution. Okay, 1 over q max minus infinity to infinity. Oh, sorry, to t. And it's to t because the ISF is assumed to have a step function, right, from causality. Yeah, okay. Gamma of tau, it of tau, d tau. Okay. And we actually did this in the ISF video already. So this kind of simplifies because the only one term really matters when k equal to m, or when m equal to k in this expansion. You can go watch that video. But only one term essentially comes out, and you can show that this is approximately equal to 2q max delta omega times sine of delta omega t plus gamma k minus theta k. Okay. All right. Since we already did till here, we've pretty much done it already, so I'm not going to expand on it. And this essentially acts like so since this is a single sinusoid, it acts like a single tone phase modulation on top of the signal, right? So this function, now we're looking at this part. So we've derived this. So now this looks like phase modulation. And as long as the signal is weak, which means this IT is small, then you can show, which I'm not going to derive here, that V of t comes out to be approximately some VH1, which is some amplitude term, omega naught t plus theta plus phi of t. Yeah, so this phi of t is, now we put this entire expression in here, and then we expand it out. And you can show approximately, actually, this is exactly an equal to, it's not approximately. And you can show that this is approximately equal to VH1 cosine of omega naught t plus theta plus VH1 IT CK over 4 Q max delta omega times cosine of omega naught plus delta omega times t plus gamma k plus theta minus theta k minus VH1 IT CK over 4Q max delta omega times cosine of omega naught minus delta omega times t minus gamma k plus theta minus theta k. Okay, so what does this mean? So this just means that your output is now modulated by two phase modulation sidebands, right? So we took some arbitrary voltage function and we added this phase in, and that voltage function had an amplitude and a phase of its own. We added phase modulation to it. So we get the voltage function back, the original sinusoid back, plus two sidebands, one at omega naught plus delta omega and one at omega naught minus delta omega. And they each have their own amplitude and phase, right? So each sideband has an amplitude and phase. And that amplitude and phase is essentially the transfer function from the input to the output, right? So the input had this amplitude and this phase, and the output has this amplitude and this phase, right? So if you remove this phase term, we get the transfer function's phase. If you remove this amplitude term, we get the amplitude of the transfer function, right? And that's essentially it. So from these equations, we can say that the modulus of the transfer function for the k minus 1th term is VH1 CK over 4Q max delta omega, and the angle of h of k minus 1, so it is theta minus theta k. Okay, so let's quickly review what these terms are. So VH1 and theta are the amplitude and phase of the oscillator when you don't have any injection sinusoidal signal. CK are the coefficients of the ISF. Qmax, which we talked about when we talked about ISF, is the maximum charge swing. Delta omega is the offset frequency, and theta k is the phase component of the ISF Fourier series, right? So from these expressions, we can find what is CK, right? So we know that CK is nothing but 4Q max delta omega modulus of h of k minus 1 divided by 4 VH1, and theta k is nothing but theta minus angle of h of k minus 1, right? Okay, now that we have CK and theta k, we can go back to the ISF and we can plug it back into this expression, right? Where I guess here it's Cm and theta m. This should actually be m, not n. Okay. Yeah, so We go back and plug it into that expression, and we end up with the actual expression of the ISF in terms of these transfer functions, which come from the periodic transfer function, right? PXF, that is. So let's write it out. Gamma of t equal to 1/2 for Q max delta omega modulus of h of k minus 1 divided by VH1 times cosine of theta minus angle of h of minus 1. Right, actually this should just be h of minus 1, not k minus 1, because k is 0 for this term. Okay, that's that. And then plus summation k equal to 1 to n, is the number of terms that you want to take, n is, times 4q max delta omega modulus of h of k minus 1 divided by VH1 cosine, maybe I'll say times cosine of k omega naught t plus theta minus angle of h of k minus 1. Okay. So that's the ISF, right? It looks long, but it's actually fairly simple Fourier series, right? And we will now simulate these transfer functions, put it into these expressions, and compute the ISF. Okay, so hopefully that's clear. Let's quickly open Cadence and I'll show you how to set this up. Okay, so if you open up, I guess, any oscillator, I guess we did this in the past where we simulated an oscillator's ISF in transient simulation. So I'll just open up the same simulation setup. So let's make a copy of that. PXF, I'll call it. Okay, so we open up the schematic and this was our cross-coupled oscillator. And we had an injection signal pulse here when we did the transient simulation. So what we'll do is we'll replace this. I'm going to delete that. And then you want an I sign, analog library, I sign. And then you can leave all of this blank, in fact. Okay, so rotate it, put it on there, and then let's save that. That's the only change you need to make. So essentially, we want to calculate the ISF for this input current to the output differential output nodes. Okay, and ISF is a transfer function, so you have to kind of specify the inputs and outputs. Here I'm specifying it as this and that. You can also look at the tail current ISF and so on. But okay, so what I will do is load an earlier state just to get the these variable values. Then we can delete all of this. We'll create a new one. Okay, so go to analysis and then select PSS. We'll do harmonic balance. I think shooting also should work, but I'm just going to do harmonic balance for now. So beat frequency is F0, which is close to or approximately what your signal oscillator's frequency should be. And then I want to do maybe 50 harmonics, make it conservative. You can leave this blank, specify that it's an oscillator, and then select the nodes. So this is your output, right? Select that to be output. So if you want output somewhere else, then you have to select a different selection here. Okay, and that's it. Hit OK. Then go to setup, and then we'll set up the periodic transfer function. Relative harmonic is 1. So this is your omega naught, right? And the delta omega is, let's set it to 10 kilo just to keep it close. Okay, so now you have your omega naught plus delta omega. That's what this is setting. And then we'll say again 50 sidebands. And then we select the positive and negative terminals. Okay, and then hit OK. All right, that's it. Run the simulation. Once it's done, go to results, direct plot. So there are a couple of things we'll plot here. So first, we'll plot the voltage waveform in time domain. I'll say differential nets, and I'll select my outputs. So that's nice. That's the voltage waveform. I want to add it to outputs. So I'll add it. And then I also want to plot the spectrum, and we'll actually need the spectrum to calculate the ISF, right? Because we need to calculate what is the magnitude and phase of the original oscillator from periodic steady state. So that's what I'm doing here. I'll just plot the magnitude, because actually when you export the magnitude plot, it also exports the complex magnitude. So just say replot. Okay, that's good. And next we'll go to PXF, transimpedance, because you're going from current to voltage. Again, magnitude, and then says select the current source. Select this. It's blank, but that's fine. Don't worry about that. Close this, and then you can plot it now, and you'll actually see it's not blank now, right? There was some bug there, basically. So the problem now, although, is that you can't really put your cursor on this because it's a complex function. Some issue in Cadence, I think, but when we export these functions, we should be fine. So what we'll do now is export these. So I've made a folder, and I'll export them as VCV files. So I'll say this is vtime, save that. Then you also want to save this, which is the spectrum, complex spectrum. And then this is the complex transfer function, right? So this is essentially saying at this input, let me zoom in maybe. So it's saying at 10, there should be two sidebands here, which you cannot see because it's very close. Maybe here you can see that they're actually not here. So yeah, here there should be two sidebands. You can't see them. Maybe what I'll do is to show you, I can just plot the real part. So let's say real, and I don't want to add it to outputs, and then replot. Let's delete this. So if you zoom in, you will actually see that they should be two. See, there's one sideband there at 20.139, and both look almost the same. But if you look at, one of them is 13921 and one of them is 13919, right? Because they're 10 kilohertz apart. So here also there should be two sidebands. So yeah, one is negative and one is positive, right? So that is essentially the transfer function from the positive and negative frequency components of each of the input harmonics, right? With an offset. And they all should have that. So you can see they kind of level out after a point, but yeah, this is the 0th one. So this will only have one sideband. And then these will have two. This is k equal to 1 and minus 1. This is k equal to 1 and 2 and minus 2, 3 and minus 3, and so on. Okay. So let me replot that, and then we'll export it. I think I already exported it, but okay. So I exported these three. So now what we'll do is go on to MATLAB. I have a code here, which I've written out. I already uploaded this code. So if you want to, you can go to my website, go to resources. So this is a website, and I have it here. So you can download the code from this link. Okay. This should take you to a Google Drive. And then I have the code, and I also have this import file function. So download these two things. I'll run you through the code, but essentially, this is what's going on. So we've said number of harmonics is 50, and then we're extracting the spectrum using this import file function. And I am extracting what's the maximum value of the spectrum, right? That's where the oscillation is. And then what's the frequency of that maximum value and the time period, right? So that's F naught and T naught. And Q max is something that, if you go back, go to the notes section, and then ISF simulation notes from the ISF simulation video. And here we actually calculate Q max for this situation, which is around 84.1 femtocoulomb, right? So that's what we'll use, 84.1 femtocoulombs. And VH1 is the amplitude that we get from the spectrum, right? So although the spectrum we extracted, so let me clear everything. So let's actually do this. Okay. Oh, sorry. Okay, so if you go to the spectrum data, when we exported it, we exported only magnitude, but actually what it exports is the real part and the imaginary part, cadence, right? So from that, you can get the magnitude and the phase of the spectrum at the harmonic, at the main harmonic, which is the second. That's what this 2 comes from, right? Okay, and then we also import the H complex, which is the complex transfer function, the PXF transfer function. And then we get the magnitude and phase part from that. Okay, and then you have the input frequency is, I am extracting it from this H complex as well, because let's go into it and look at it. Okay, so there we go. So I'm saying, okay, the input frequency is all of these frequencies, right, from H complex. And then I say, what's the minimum value? And the minimum value should be delta F, right? Yeah, and then, of course, when you extract it from Cadence, if you remember, or if you noticed, let's go back here. It's only extracting the absolute value of the input frequency. That's what this abs in is. You can change that, but since it's absolute value, we need to make it positive and negative, right? So that's what I'm doing here. So if you see F in, let's just do this, then it's only positive. So it decreases all the way to delta F and then again increases, right? But after running this, you'll see that F in now is, yeah, there's negative frequencies all the way down to 1 kilo, and then you have the positive frequencies. Okay. And then I want to calculate what is this P value, which is K minus 1, right? And then if you look at the equations that we derived, then the P is F in minus delta F minus F naught divided by F naught. Okay. So let me actually open up my notes that I just wrote down. Okay, so these are the notes we just wrote down. And if you see here, the input frequency is given by P omega naught plus omega naught minus plus delta omega. So we have F in, which should be over here. And then we have this. So from this, you can extract P, which is what I'm doing here. Right. And of course, since there's some numerical error, you only get an approximate value of P. Right. But you can just round it out, which is what I'm doing here. Right. So once you round it off, you'll see that P should vary from minus 50 up to plus 50 because we set up 50 harmonics, right? Okay. And then delta omega is from delta F, omega naught is from F naught. And of course, in one case, I'm using pi, in another case, I'm using 180 because I use, I guess, radians and degrees in different locations, but you can change that if you like. You have to be a little bit careful about where you're using radians and degrees, though. Since here I'm going to use cosine D, I use degrees. Anyways, so then T, I set up about 1,000 points going from 0 to T naught. And then I initiate ISF with 0. And then I go through a loop essentially, and I calculate this expression, which comes directly from the last expression here, right? 4Q max delta omega modulus of H over VH1. And that's exactly what this is, 4Q max delta omega modulus of H, which is this. And I extract H for the value where P from this P is equal to K minus 1, right? Because we want H of K minus 1. And we know K minus 1 is equal to P divided by VH1. And then the angle part is this one, cosine K omega naught T plus theta minus angle. Cosine K omega naught T plus theta, which is VH1 of the phase of VH1, minus the angle. Okay, and the scale factor is essentially to make sure that when I go through the loop, the first term, which is this term, has a 1/2 in front of it. So then if you do that, then you can bring it into the summation, right? So that's kind of what I'm doing. And then I run the summation, and then I calculate, actually don't use these, but I plot as a function of time the ISF. And then I also have the ISF from the transient response, which we calculated earlier, which I've saved into a file here just to compare them. I have the time domain from that, but that was not done with such high resolution in time. So I'm resampling it in time to the current time samples. And okay, there's a negative sign here, and I noticed that actually the ISFs line up very well when I add this negative sign. I think that's because when I calculated it using transient response, I used the wrong phase. I used like a negative of the right phase, but it really doesn't matter. We'll see that when we use ISF, it's the shape that we care about. The negative sign or the phase sensitivity, whether it's positive or negative, doesn't matter. In fact, when we do use the ISF, what we really care about is the C naught term. If you remember, This C naught term is what really matters, right? That's what determines the flicker noise down conversion. That's the big insight that ISF kind of gives us. So if you look at this expression, C naught is h of minus 1. So we really only care about this term. So we don't have to go to MATLAB and do all this. You can just extract this harmonic when you simulate the ISF using PXF in Cadence directly and look at what's happening to this h of minus 1 term, right? And then if you want to run a parametric sweep, you can plot what is h of minus 1 as a function of a parameter that's sweeping and then see if it's going up or down, right? So that's when we go to using ISF into design of oscillators and how it's actually helpful, we will focus on this part so you don't have to go through this whole MATLAB implementation. But anyways, so that's why I have the negative sign there. And here I'm shifting the transient simulation of the ISF in time so that they line up, because of course the time reference that we used when we did the transient simulation is not going to be the same as what we do, what the time reference of this PSS. So that's what this circ shift is doing. And then finally, I'm also plotting the time domain voltage waveform, which we extracted just now. Okay, and then I change the properties of it. So that's what the code is doing. So let's actually run it and see what happens. Okay, so once you run it, you see that the transient response of the ISF is the orange dashed line. What we calculated just now is the PXF response, the blue line, and then the yellow line is the time domain voltage, right? And obviously, there's very good agreement between the two. You don't have to use, so for example, here I haven't used all 50 harmonics. I've only used 20 harmonics. You can even use maybe just 10 harmonics and get away with it, but it's pretty much instantaneous, so it doesn't matter. And we saw that even the simulation barely takes not even a second, right? Yeah, like what, 1 second. So it's much, much faster, and we've gotten the right ISF. So that's about how to simulate ISF. We can quickly look at PPV. We don't have to do any theory, luckily, because PPV is already implemented in Cadence. So I'll show you, just go to PSS, you can click on options, output, scroll down, and then say yes, save oscillator PPV, hit OK, OK, and then run this. So once it runs, you can just open up any kind of plotting window, go to browser results, open results, click on PSF, and then here you'll see PSS time domain PPV, click on that. And that's it. So you have the PPV at different output nodes, right? So for example, at X, let me actually replot it so that I want this to be empty. Okay. Browser results, open results, PSF, PPV, click on X. So that's the PPV of X. That's of Y, and net 3 is the sort of this tail current node. And that should be twice the harmonic, right? So that's the PPV. And of course, you can kind of send this to, I mean, as an example, I can show you send to calculator. And then from calculator, you can send it to ADE so that it plots from the ADE. Okay, there we go. So that's the PPV, right? So it's much easier, of course, but you can choose, I guess, which function you want to use. And we'll use both maybe in the future as we go through, and we'll see how to use these ISF and simulated ISF and PPV. So hopefully that covers what I wanted to cover. If you have any questions, you can leave them in the comments. The notes are uploaded and the code is also uploaded. So in the next few videos, we'll look at how to use the ISF to kind of reduce flicker noise, up conversion, and maybe improve the oscillator design for this cross-coupled oscillator. And then slowly we'll move on to other topics as well. Okay, hopefully you're excited about that. Thank you so much for watching, and I'll see you in the next one.